Somewhere in NASA's Jet Propulsion Laboratory, there's a folder of data that scientists have been staring at for years, unable to fully agree on what it means, because every explanation they try to apply to it runs directly into the same wall. According to the physics we currently understand, what this data shows should not be possible. Not unlikely, not surprising. Genuinely, according to decades of peer-reviewed models built by some of the best physicists on the planet, impossible. And the source of that data is not a new telescope, not a satellite, not some billion-dollar next-generation observatory. It is a machine that was finished being built before most of the people now analyzing its results were even born. It is currently more than 15 billion miles from Earth, so far away that its radio signal, moving at the fastest, speed anything in the universe is allowed to travel, takes over 22 hours just to arrive. This is the story of what Voyager 1 confirmed at the very edge of our solar system, a finding so strange that when it was published, the scientific community did not describe it using the careful, neutral language research papers usually use. They used a different word. They called it impossible. I am your name, and this is your channel. Subscribe now if you want more stories like this, because we are just getting started. To understand why this discovery broke the rulebook, you first have to understand what the rulebook actually said. Voyager 1 launched on September 5th, 1977, on a mission that NASA planners originally expected to last 4 or 5 years. A modest tour past Jupiter and Saturn designed to capture close-up photographs and basic measurements before the spacecraft drifted into silence sometime around 1981 or 1982. T did not go quiet. It returned the first close-up images of Jupiter's surface ever captured by human technology, flew past Saturn using each planet's gravity as a slingshot to gain more speed and reach farther than any previous spacecraft, and kept transmitting long after its planned mission had ended. By the time it crossed the heliopause in 2012, Voyager 1 had already spent 35 years exceeding every expectation placed on it, and the discoveries that followed at that boundary would end up mattering more than anything imagined needing to measure. For decades, before Voyager 1 ever got close to interstellar space, physicists built detailed mathematical models describing what the boundary of our solar system should look like. This boundary is called the heliopause, the outer edge of a colossal bubble created by the solar wind, a constant stream of charged particles pouring outward from the sun in every direction. That bubble is not decoration. It is the thing that has kept our entire solar system, every planet, every moon, every living organism that has ever existed, wrapped inside a layer of relative protection from the harsher, more energetic environment of interstellar space. The models built to describe the edge of that bubble made a very specific prediction. They said the transition from the solar wind on the inside to interstellar space on the outside should be smooth, should be gradual, should behave the way a river slowly blends into the sea, particles thinning out calmly, temperatures shifting gently, one environment fading into the next in an orderly, predictable way. That is what the mathematics said should happen. That is what generations of astrophysicists built their careers expecting to eventually confirm once an instrument finally got close enough to check. Voyager 1 got close enough to check in 2012, becoming the first human-made object in history to physically cross that boundary and continue transmitting from the other side. And what it found broke the model immediately. Instead of a slow, calm blending of environments, Voyager 1's instruments recorded particles slamming into each other, at velocities approaching a meaningful fraction of the speed of light, generating temperatures in that supposedly cold, empty transitional zone reaching approximately 30,000 degrees Celsius, not inside a star, not inside any burning object anywhere nearby. At the outer edge of our own solar system, in a region multiple generations of physicists had modeled as one of the quietest, coldest, most uneventful stretches of space spacecraft could possibly pass through. Some of the researchers who studied this data afterward began describing the region using a phrase that has nothing to do with the sterile, careful language usually found in astrophysics journals. They called it a wall of fire, and they meant it as a literal description of the energy involved, not a poetic flourish. A concentration of ultra-energetic charged particles forming what amounts to a physical barrier at the edge of everything human civilization has ever called home. That alone would have been enough to force a rewrite of the textbooks. But it was not the only rule Voyager 1 broke at the boundary, and the second one may be even harder to explain away. For just as long as physicists had modeled the heliopause as a smooth thermal transition, they had also modeled it as a clean magnetic separation. Inside the bubble, the theory went, space is dominated by the sun's own magnetic field carried outward by the solar wind. Outside the bubble, space is dominated by an entirely separate magnetic field, the ambient magnetic field of the wider galaxy, unconnected to anything our star produces. Two distinct magnetic environments, cleanly divided at the boundary, like two different countries separated by a national border with no overlap between them. This was not a minor detail in the model. It was one of the foundational assumptions underlying how scientists understood the heliosphere's structure. When Voyager 1 crossed through and began transmitting magnetic field readings from the far side, that clean separation simply was not there. Instead, researchers found the sun's magnetic field lines, compressed and carried outward by the solar wind, actively interacting with the galaxy's magnetic field on the other side of the boundary, in a documented process called magnetic reconnection, where field lines from two entirely different sources physically link, rearrange, and release energy in the process. The solar system and the surrounding galaxy were not supposed to be magnetically connected at all. Voyager 1's data showed that, in specific and measurable ways, they are. Think about what that actually means, because it is easy to let a sentence like that slide past without absorbing the weight of it. Every model of how our solar system relates to the wider galaxy, every calculation of how protected we are from the high-energy radiation drifting through interstellar space, every assumption about where our home ends and the rest of the galaxy begins, was built on the premise that these two magnetic environments stay separate. Voyager 1's instruments found direct evidence that, at least in places, they do not. That single finding is why some of the scientists reviewing this data were not comfortable simply filing it away as an interesting anomaly. It touches the foundational architecture of how the heliosphere is understood to function, and it opened a question nobody had a ready answer for. Then, starting in 2017, Voyager 1 handed researchers a third piece of evidence, and this one did not arrive as a single dramatic crossing. It arrived as something quieter and, in some ways, stranger, a persistent hum. The plasma wave instrument on board began detecting a narrow continuous emission in the plasma of interstellar space. Not a single spike, not a one-time burst that could be dismissed as sensor noise, but a signal that kept showing up year after year across a stretch of interstellar space measuring more than 900 million miles, roughly 10 times the entire distance between the Earth and the Sun. Researchers who published their analysis of this signal in the peer-reviewed conclusion that directly contradicted decades of prior modeling. Interstellar space, they wrote, is not the smooth, uniform, quiet void that theoretical models had long described. It has structure, texture, and turbulence at practically every scale, from distances measured in meters to distances measured in millions of miles. The empty space between stars, it turns out, is not empty in any meaningful sense of the word. It is, in the words used to describe the data, alive with a level of motion and complexity that no instrument had ever been positioned to detect before, simply because no instrument had ever been sitting inside it. Every previous measurement scientists had of interstellar plasma density came from isolated indirect snapshots, triggered occasionally when a massive eruption from the sun sent a shock wave rippling all the way out past the heliopause. It was, researchers have said, something like trying to understand the weather across an entire continent using a single thermometer checked once a year in one city. What Voyager 1's persistent signal provided instead was something closer to a continuous feed, a running record of what interstellar plasma is actually doing day after day, year after year. The first time in human history anyone had that kind of ongoing window into the space between stars. Here is where the scientific community still does not have a finished answer, and it is worth being honest about that, rather than pretending the mystery has been neatly solved. Researchers analyzing this persistent plasma signal have identified two competing explanations for what is actually causing it, and years later, they still have not been able to determine with certainty which one is correct. The first possibility is that the signal comes from thermally excited plasma oscillations, essentially the natural vibration of charged particles reacting to their environment. This would be an important discovery, but one that could still fit inside existing physical frameworks without requiring them to be torn up and rebuilt. The second possibility is something called quasi-thermal noise, a distinct physical mechanism that would carry information about the density and temperature of interstellar plasma in a fundamentally different way, one that would force a substantial revision of the model scientists currently use to describe the interstellar medium. Telling these two explanations apart requires either more data from Voyager 1 itself, which is producing less of it every single year as instruments are shut down to conserve its dwindling power supply, or an entirely new mission purpose-built to study interstellar space directly. No such mission currently exists. No such mission is currently funded. If one were approved and launched today, it would not reach the heliopause for at least another 25 years. Now here is the part of the story that makes this urgent rather than simply fascinating, because Voyager 1 very nearly lost the ability to tell us any of this at all. In 2023, the spacecraft began transmitting something engineers at the Jet Propulsion Laboratory had never encountered in over 4 decades of operating this mission, a signal that kept arriving, steady and unbroken, but composed of complete gibberish, corrupted, unreadable code, coming from a spacecraft that was clearly still alive and still trying to communicate, but whose message had become impossible to decode. For 5 months, the team worked the problem with a level of patience most engineering disciplines never require. The eventual cause was almost absurdly small, measured against the scale of the crisis it caused. A single memory chip inside the spacecraft's flight data system had physically degraded after nearly 5 decades of continuous exposure to cosmic radiation, corrupting the exact portion of software responsible for formatting the data before it was transmitted home. Fixing it required something engineers do not normally have to consider, because the broken component sat roughly 15 billion miles away, well beyond the reach of any repair mission, reachable only by radio signals that took 22 hours to arrive and another 22 hours for any response to come back, a minimum of 44 hours to complete a single exchange of information for a problem that might take dozens of exchanges to solve. Engineers eventually determined the corrupted code could not be repaired in place, but it could be relocated, split into smaller sections, rewritten to function from new locations, elsewhere in the spacecraft's limited memory and carefully reconnected. It was, in effect, a form of remote surgery performed across a communication delay measured in days on a patient built in the 1970s that nobody could physically reach. In 2024, Voyager 1 came back online, and the very first thing it resumed sending was more evidence of that same unexplained plasma turbulence in interstellar space, the discovery that had helped make this spacecraft's data so valuable in the first place, and the reason its recovery mattered as much as it did. Think about what that engineering process actually looked like from inside the control room during those 5 months. You look at a fragment of corrupted data. You form a theory about what might be wrong. You write a careful set of instructions designed to test that theory without risking further damage. You transmit those instructions across 15 billion miles of empty space. You wait 22 hours. You receive whatever the spacecraft manages to send back. You analyze it, discover something slightly different from what you expected, form a new theory, write new instructions, and send them again, knowing that a single incorrect command sent once across that distance could end the mission permanently with no chance of recovery. That was the reality facing the team at the Jet Propulsion Laboratory for 5 straight months in 2023, working through one of the most delicate remote repairs ever attempted on any spacecraft. On hardware, nearly 5 decades actually working on beyond the numbers old, with no ability to see what they were arriving in each delayed transmission. That near-death experience is directly relevant to what is happening right now in 2026, because the clock on this mission has never stopped running. Voyager 1 draws its power from 3 radioisotope thermoelectric generators, devices that convert the heat released by slowly decaying plutonium-238 into usable electricity. At launch in 1977, these generators produced roughly 470 watts of power. Today, nearly half a century later, that output has dropped to somewhere around 250 watts, losing approximately 4 watts of capacity every single year. Of the 10 scientific instruments Voyager 1 originally carried, 7 have already been permanently switched off, not because they stopped working, but because there is no longer enough electricity to keep them running alongside everything else the spacecraft still needs to function. Earlier this year, the low-energy charged particle experiment, one of the instruments that had been gathering data almost continuously since 1977, was shut down for exactly that reason. A difficult decision made by a team that has spent years carefully sequencing which instruments to sacrifice and in what order, knowing there is no way to switch anything back on once it goes dark. Except, in this specific case, there may be. NASA engineers are currently testing something reportedly referred to internally as the Big Bang procedure, an experimental attempt to restructure how power flows through Voyager 1's remaining systems, in order to squeeze additional electrical capacity out of components that are currently running less efficiently than they could be. Because any misstep in reconfiguring a nearly 50-year-old spacecraft with no possibility of a manual override carries real risk, the team tested the procedure first on Voyager 1's twin Voyager 2, which has somewhat more available power and sits closer to Earth, making a potential failure less catastrophic if something went wrong. If those tests confirm the procedure is safe, the same approach is planned for an attempt on Voyager 1 itself. And if it succeeds, there is a real possibility that the very instrument just switched off could be brought back online, giving this aging spacecraft a genuine second chance to keep collecting the exact kind of data that keeps forcing scientists to rewrite what they thought they knew about the edge of our solar system. And there is a very specific date already locked into the calendar that makes this moment matter even more. On November 18th, 2026, Voyager 1 will cross a threshold, before becoming exactly 1 light day away from Earth, a distance so vast that a radio signal traveling at the absolute speed limit of the universe will take a full 24 hours just to arrive, and another 24 hours for any reply to make its way back. Every hour that passes after that milestone, the spacecraft moves roughly another 38,000 miles farther into darkness, carrying its instruments, its dwindling power, supply, and its golden record of Earth's sounds and languages deeper into a region of space that remains almost entirely unmapped by any direct human instrument. Every hour that passes after that milestone, the spacecraft moves roughly another 38,000 miles farther into darkness, carrying its instruments, its dwindling power supply, and its golden record of Earth's sounds and languages deeper into a region of space that remains almost entirely unmapped by any direct human instrument. That record, a gold-coated copper disc carrying greetings in 55 human languages, recordings of rain, ocean waves, human laughter, and 90 minutes of music drawn from cultures across the span of human history, will keep traveling long after Voyager 1's instruments finally fall silent sometime in the early 2030s. There's no friction in interstellar space to slow it down, no atmosphere to burn it up, nothing strong enough to meaningfully pull it off course. It will simply keep moving in a straight line, carrying physical proof that a species once existed here, curious enough to ask what lay beyond its own solar system, and patient enough to build a machine capable of actually finding out. Here is what deserves to sit at the center of this entire story. The scientific community does not use the word impossible casually. It is not a word that appears in careful, peer-reviewed research, because it makes for a better headline. It appears because the data genuinely does not fit inside the frameworks scientists spent decades building. Frameworks based on the best available theory, the best available mathematics, and the best available understanding of how a star's magnetic influence should behave at the edge of its reach. Voyager 1 walked past every one of those predictions and returned measurements of temperatures that should not exist there, magnetic connections that were not supposed to be possible, and a persistent structure in supposedly empty space that no model had prepared anyone to find. And it did all of this using